We're continuing on section 4.7, example 6. A landscape architect wishes to enclose a rectangular garden of area 1,000 square meter. On one side will be a brick wall costing $90 per linear meter, and on the other three sides will be a metal fence costing $30 per linear meter. What dimensions minimizes the total cost? And so what you want to figure out, the minimize the total cost tells you that your goal function is the cost, and the constraint is the area. We want to have the 1,000 square meter area. And so write down the cost and write down the constraint. Constraint is there, if there are two sides, x can be one length, y can be the other length, and x times y has to be 1,000. Then the cost is going to be basically 90 times one length and 30 times 2 times another length plus that first length, and so that's how you know it's 90x plus 30 times 2y plus x. And then you replace y by solving for x in the constraint. And then remember that domain in this case is going to be all the positive numbers, and 0 is not included because c of x has the point of discontinuity as at x equal to 0, or domain is not defined at x equal to 0. Take the derivative. Derivative in this case is 120 plus and minus 60,000 divided by x squared. Do the common denominator right there, and then from there you can solve for the critical values. 0 in the denominator doesn't count because 0 also is not in the domain. So when you find the critical values, you find square root of 500 is a critical value, and since this is not a closed domain, closed interval method, we can do a closed interval domain and closed interval method. We have to use another thing. You can use a first derivative test and then find that the cost is decreasing in an interval between 0 to 5 square root of 500 and increasing on the interval square root of 500 and infinity. And so the absolute minimum is going to, again, one critical number in the domain, and that critical number is a local minimum. There it has to be an absolute minimum, and so the absolute minimum happens there, and then you calculate how much that cost is by plugging it back into the cost function. And so that's another example, and let's have blank margin on top and bottom of 10 centimeter, 10 centimeter on the bottom also, and then you want to have 6 centimeter on the side, and then this would be the printed area. So whatever x and y you get, then x minus 20 and y minus x minus 12 and y minus 20 is going to be the dimension that you get for the printed area. Other things to notice: x has to be bigger than 12 and y has to be bigger than equal to 12, and y has to be bigger than equal to 20. And so the printed area is going to be x minus 12 times y minus 20 in parentheses, otherwise it would not multiply correctly. And again, the constraint is going to be x times y equal to 60,000 square centimeter. Replace y in here by how you solve it from the constraint. So y over here is 6,000 divided by x, replace it right there, and this is the equation that you get. It might be easier to actually use a product rule here rather than multiply it through that, rather than foiling this, but either one is okay. And so you can either multiply through then take the derivative, or basically use the product rule. But in any case, you figure out that the domain is the minimum x that can be is 12, and the maximum x can be is when y is minimum. Y minimum is 20, and that would be 6,000 divided by 20, which is 300. So domain is 12 to 300, and it's a closed interval. So I can use the closed, or we can use the closed interval method. Anyway, take the derivative and simplify, and you end up with this expression. So you see that within the domain there is only one critical number, and that's 60. So evaluate the printed area at 60, evaluate the printed area at 12, evaluate the printed area as 300, and see that the maximum printed area happens at the critical number, and then you can calculate the maximum printed area. It happens at 60 times 100, and that's actually the value is 3,840 square centimeter. Now I click here question 4 for the for the curve f of x equal to 1 plus 40x to the power 3 minus 3x to the power 5, what is the maximum tangent line slope? Let's pause. Now we're trying to find the maximum of the function f prime of x equal to 120 x squared minus 15x to the 4th. This is the objective. And then if I take the second derivative of this, I get 240x minus 60x to the power 3. Now factor 60x, and 4 minus x squared is the second term. So the critical numbers for f prime, which is the objective function, and we took the f double prime, so we can find the derivative of the objective function, are 0, 2, and -2. Make a number line for f double prime, which is the derivative of the goal function, and then find the signs for f double prime. For f double prime, as we go toward the negative infinity, f double prime is going to be a positive value, and between -2 and 0 it's going to be a negative value. Between 0 and 2 it's going to be a positive value, and as x after 2, as x goes to big numbers, but big positive numbers, it's going to be a negative value. So I can see that by first derivative test, that's first derivative test where you see f double prime. Why? Because goal function was the first derivative. And so in here you see that at x equal to -2 and 2, you have a local maximum. Because it seems like there's the trend is from here going down and from here going down, it seems that one of these can be, it has to be the absolute maximum. And so over here, when you come back to the f prime and you plug in, if I plug in 2 or -2, both of them are going to give me the same answer. And so let's plug it in. F prime at 2 is 120 times 4 minus 15 times 16. And when we calculate this, we end up with 240.